Let's have a look at this Moore machine example. What is required for you is to design a system that controls an elevator, a two-level elevator. And the elevator has one input and one output. The input indicates the level that the user wants to go to, and the output indicates the current level. Okay, so the input could be either a 0 or a 1. The 0 represents that the user is requesting to go to floor 0, and the 1 requesting to go to floor 1. And the Z similarly has the same indication, whether it's a 0 or a 1. So we receive a bunch of input bits. Each of them represents the value of X at the current time slot, at the current clock cycle. And what is required is to design the state diagram of this Moore machine. So how do you do that? We start with a state called S0, and it represents being at state at the level 0. Okay, and definitely the output is going to be 0 at that particular state because we are at level 0. So what if I receive an input of 1? An input of 1 means that the user is requesting to go to state S1. So I have to create another state and call it state S1. And in that case, the output of that state is 1, indicating that we are at state S1 at the moment, which is level 1. Okay, what if you have an input of 0? Then in that case it loops back because we are currently at state S0, which means that level 0, that's the 0th floor, and thus the user should remain at that particular level and should not go to any other. The elevator should not move. Okay, and similarly we need to go to state S1 and study what happens if we have an input of 0 and what happens if we have an input of 1. So if for an input of 0, then we go back to state S0, representing that we are now moving the elevator from state S1 to state S0, and the input of 1 represents that we want to be at state S1, we want to remain at that same level, so we do not go anywhere and we loop back at that level. Okay, that simple example is a two-level elevator. What if we make it a little bit more difficult and we have a 4-level elevator? So we have 4 floors and we want to control the elevator such that when the input is 0, 0, so in that case we have 2 bits of inputs, we do not have just 1. 0, 0 represents that the user wants to go to floor 0. And 0, 1 represents to go to floor 1, and so on and so forth. And similarly, we have 2 output bits, Z1 and Z2. And as you can see, we're going to actually merge them or concatenate them. So the inputs of Z1, Z2 that's actually the outputs. Z1, Z2 represents, it could be either 0, 0, 0, 1, 1, 0, 1, 1. When Z1, Z2 equals 0, 1, this means that Z1 equals 0 and Z2 equals 1. And it means that the user is currently at level number 1, at floor number 1. Okay, so that's the convention. And we have, similarly, we have 2 bits of inputs, X and Y. Each one could take either a value of 0 or a value of 1. And by convention, we are concatenating these XYs so that we can make the problem a little bit easier. And thus, the input 0, 0 represents that the user is requesting to go to floor 0. And it means that X equals 0 and Y equals 0. So note that in the problem it gave us a hint which says that the elevator cannot jump any floors, which means that if we want to go from floor number 0 to floor number 2, for instance, then we should first go to floor number 1 and then from 1 to 2. Okay, let's design this problem. So you begin with a reset state, which is state S0, and this state has an output of Z1, Z2 equals 0, 0. In that case, remember that I need to specify the outputs so that I can tell the grader which is which. Z1 is the first one and Z2 is the second bit, is the least significant bit. If I receive an input of 0, 0, then I need to loop back at the same S0 state, which represents that I'm currently at floor 0 and I should not let the elevator move. What if I receive an input of 0, 1? Then definitely I need to go to another state, and that's why I create another state and call it S1 with an output of 0, 1, and that's the arrow that represents going from that state to the current S1 state. Okay, so what if I receive an input of 1, 0 while I'm at state S0? Well, in that case I need to go to state S2, but of course we cannot jump the floors, so that's why we need first to go to state S1 and then from S1 to S2. Okay, so I'm going to write down a 1, 0 at that arrow to represent that this arrow, it goes from state, lets the system go from state S0 to S1 if an input of 1, 0 occurs. If we see an input of 1, 0, then we're going to go to state S1. Okay, and then if we want to go to state S2, well, definitely if we go to state S1, it's not the final state that you want to go to. 1, 0 represents that you want to go to state S2. So when you go to state S1, then in that case you have another arrow that goes to state S2 to represent that the system is finally going to the requested floor. Of course, you cannot have an arrow that go directly from state S0 to state S2. Okay, because the elevator cannot jump any floor. Okay. What if you have an input of 1, 1? Then you need to go to floor 3. In that case, you have to first go to state S1 and then state S2 and then finally to state S3. So actually this arrow is really a triple arrow. It represents the 0, 1 and 1, 0 and 1, 1 at the same time. And the reason why I make 3 arrows combined together is just to make the system a little bit easier to read. So this arrow represents I'm going to go from state S0 to state S1, whether I receive an input of 0, 1 or a 1, 0 or a 1, 1. Okay, let's move on to state S1. Why did I move on to state S1? Because I have finished already state S0. What does state S0, why did I say that I have finished state S0? Because I have taken all of the possibilities that could happen at state S0. The inputs could take either a value of 0, 0, 0, 1, 1, 0 or a 1, 1. So I do not have any other possibility. That's why I need to begin studying state S1 since I finished state S0. At state S1, I could receive an input of 0, 0. Okay, in that case, it indicates that we need to go to level 0. Okay, or I could receive an input of 0, 1. In that case, I need to loop back at the same state, or receive an input of 1, 0 or a 1, 1, which is represented by this arrow. Okay, and then I go to state S2, study that state. If I receive an input of 0, 0, then I go to state S1, and then an input of 0, 1 lets me go to state S1, okay? And in that case, remember that this 0, 0 is, yes, it's going to let us go to state S1, but it's not going to be the final state, because when I reach S1, the machine is going to look at the input and it is going to find it still 0, 0, so it's going to let the elevator proceed to state S0. Okay? And if I receive an input of 1, 0 at state S2, then I remain at that state. Okay? And then finally at state S3, I have the 3 arrows 0, 0, 0, 1, 1, 0 represent that we want to descend. And finally, if we receive an input of 1, 1, then we want to go to state S3, so we remain at that particular state, indicating that the elevator is not going to leave. So that's pretty much how you design a state machine for a Moore machine, and it is simple in the sense that it is systematic steps. So let me recap here these steps for you so that you can write them down and find out how to solve any Moore machine problem. The first step is to draw a bubble and call it the reset state, and then you find out what the possible inputs at that bubble is. What are these possible inputs? So if you have, for instance, 2 inputs, then you have x, y, might be 0, 0 or 0, 1, 1, 0 or 1, 1. You need to ask yourself what the next state is and what is the corresponding output of that next state going to be. And you need to repeat this question for every single input at that particular state and create states whenever needed. Okay? And in general, note that if you have 2 inputs, then you have 4 arrows. If you have 1 input, then you have 2 arrows. So in general, you have 2 to the n arrows coming out of each state. Once you finish these 2 to the n arrows, then you proceed with the following state and study it, which means that you need to repeat these steps again. Okay? And finish one. How do you know that you're done? Finish the state diagram by making sure that every state has 4 arrows coming out of that particular state, and this is an indication that you have finished your state diagram. Finally, that's a checklist for you to make sure that your state diagram is really concluded. First of all, check that all states have 2 to the n arrows coming out of each one of them. And in that case, you count these arrows as 3 arrows in our particular example. Okay. Make sure that your state diagram has a name. In that case, it's the S0 or the S1, S2, and S3. Okay. And then make sure that the inputs and the arrows are well defined on your diagram. Otherwise, we will not be able to understand your state diagram. You need to mention that Z1, Z2 is the output, or perhaps Z2, Z1 is the output, according to what convention you're working with. So if you leave it like this, then this is an indication that you're following the same convention as this. So that's why it is very important to mention this convention on your state diagram. If you didn't mention it, I won't be able to tell which one is which. Okay? And the same goes for the input as well. Once you decide one input, then all of the rest pretty much goes the same.